Okay, some more examples about counting. Here's our principles: inclusion and exclusion. If A and B is sets, the number of things in A union B is the number of things in A plus the number of things in B minus the number of things in A intersection B, right? Don't want to double count the overlap. If they're disjoint, so that this is an empty set, then A union B is just a number of things in A plus the number of things in B. And if A is a subset of U, then the number of things in A plus the number of things not in A is the entire universe. We often use that as a subtraction. The number of things in the universe minus the number of things in A is the number of things in the complement of A. And the multiplication principle, if you've got n steps and n sub I choices at the ith step, the total number of possible ways to do the activity is the product. So we'll start with a couple of counting examples that can be done with Venn diagrams. And unfortunately, apparently, I bring the notes that actually have the numbers on them, which is not ideal, but we'll see how this goes. So, example 1. Suppose you have 33 students in a class, 8 students like vanilla, 10 students like chocolate, 5 students like chocolate ice cream, and they also like a vanilla ice cream. So draw a Venn diagram to illustrate this situation. So Venn diagram, the box represents the class, that's 33 students. We have one circle for people who like vanilla, one circle for people who like chocolate. Okay, so we have to be a little bit careful. Vanilla is broken up into 2 parts. Some people like vanilla but don't like chocolate. That's these people. Some people like vanilla and chocolate. Likewise, some people like chocolate but they don't like vanilla. That's those people. And the people outside, they don't like either one. So we have to be a little bit careful about putting the numbers into the box. Vanilla, that's 8 people total, but it's split up between these 2 regions. Chocolate is 10 people total. That's split up between those 2 regions. I'm not filling in the Venn diagram yet. 5 students like both. So 5 students are actually in the intersection. They like chocolate ice cream and also vanilla ice cream. So they're in both circles. 8 people are in this entire circle. So if I have already counted for 5 of them, there must be 3 people who like vanilla but don't like chocolate. 5 people like chocolate but don't like vanilla. Out of the class, there's 33 students. We've accounted for 13 of them. So that must be 20 people don't like either chocolate or vanilla ice cream. They like chocolate mint chip ice cream. That's all great thinking people do. So we can also do this with a table. 1, 2, 3, 4 lines. I think it's 4 lines. Could be 3. Yep, 1 more at the bottom. There we go. So the last column is totals. Totals. Vanilla, not vanilla, and chocolate, and not chocolate. So same data. The total number of people in the class is 33. How many people like vanilla? This is my vanilla people. 8 of them like vanilla. How many of them like chocolate? This is my chocolate people. That's 10. How many people like both? That's 5. Right? So 8, 33, 10, and 5. Those numbers are put in. And then the argument runs pretty much the same way. Vanilla, some people like chocolate, some people don't. 3 don't. So that accounts for all 8 of my vanilla likers. 5 and 5, that's all 10 of my chocolate likers. How many people don't like chocolate? Well, 10 people like chocolate out of 33, so that means 13 don't like chocolate. 8 people like vanilla out of 33, so this must be 25. So what's the number that goes in here? 20 people, 20 plus 3 is 23. There we go. And 5 plus 20 is 25. So same data, just arranged in a different way. Like either chocolate or vanilla. How many people like either chocolate or vanilla? Can be answered one of 2 ways. Chocolate union vanilla, well, that could be 3 plus 5 plus 5, 13. 5 plus 3 plus 3, right? That's 13. you just add up all the people in the chocolate and vanilla categories and see what you get. Or how many students like neither? Well, that's 20. So you've got 33 students, 20 of them don't like either one. So the other 13, they must like either chocolate or vanilla. So we can either take 33 minus 20, and that tells me how many people like chocolate or vanilla, or I can add those up. Okay. So same kind of deal here. We'll do this as a table, Spanish and math. So some students take Spanish, some people don't take Spanish. Some people take math, some people don't take math. And then I need totals. So there's my table. 100 students, that goes down here. That's my grand total. 54 math students taking math. How many students are not taking math? Well, it must be 46. 59 are taking Spanish. How many are not taking Spanish? Well, that must be 41 then, because there's 100 students total. 29 take neither. So this is the column for not taking Spanish. This is the row for not taking math. We must have 29 students who are not taking either one. So can you fill in the rest of the table? Well, sure, right? Not taking Spanish, there's 41 students not taking Spanish. 29 of them are not taking math. That means the other 12 must be taking math, but not Spanish. So how many people taking math and Spanish? Well, what plus 12 is 54, and that would be 42. So how many people not taking math, but are taking Spanish? 42 plus what equals 59, that's 17. And there's a check, 17 plus 29 is in fact 46. So there's our table. Now we can answer all these questions. Take math, but not Spanish. Math, but not Spanish is 12. Spanish, but not math. Spanish, not math. 17. Spanish and math. That's 42. Take Spanish or math. Right? The or is telling me that there's actually 3 possibilities here. You can take Spanish but not math, Spanish and math, or you can take math but not Spanish. So 42 plus 12 plus 17, which is what, 59, 69, 71. Or, right, these 4 numbers together, that's all 100 students. If I want to know what the sum of these 3 is, I can just take 100 minus 29, and that tells me how many people are in there. You have 3 conditions, math, Spanish, and history. It's really hard to write a table for it. You really have to do this sort of as a Venn diagram. A 3-circle Venn diagram, look like this. We'll say that this is math, this is Spanish, this is history, this is the entire class of 75 students. How many people are taking math? 33. How many are taking Spanish? 34. Note, I do not put the numbers inside until I figure out which numbers are which. These 34 people are taking Spanish. Some are taking just Spanish. Some are taking Spanish and math. Some are taking Spanish and history. Some are taking all 3. So there's 4 categories for Spanish students, and you need to figure out how to break them up. So 15 students take math and history. That tells me that these 2 areas have to add up to 15. 10 students are taking Spanish and history. That tells me that these 2 numbers have to add up to 10. 25 are taking exactly 2 of the 3 courses. Exactly 2 of the 3 courses is this region, and this region. Right? Spanish and history, but not math. Math and Spanish, but not history. Math and history, but not Spanish. And 7 are taking all 3. So 7 is all 3. Right? But then history and math, there's 15 students taking history and math, so these 2 have to add up to 15, so this must be 8. 10 students are taking Spanish and history, and so this must be 3. And 25 students are taking exactly 2 of the 3, so 11, so this must be 14. Great. So, how many students are taking math, but none of the other 2 courses? We've already counted for 18 of the math students, so there's 15 here. How many students are taking Spanish but none of the others? We've accounted for 21, 24 of the 34, so there's 10 there. And how many students are taking history but none of the other? Well, we've accounted for 15, 29. Oh, my numbers are off. So we'll make this 30 are taking history. Not quite sure what happened there. But we've got 21, 29, so we have one student taking history, but none of the other courses. Okay. How many students are taking none? Well, we started with 75. We've counted 34 there, 16, 24, 34 and 24 is 58. These are all the students who are taking classes. These are all the students taking Spanish classes. That's 34, plus the 15 and the 8, which is a 23, plus a 1. So 58 students are taking one of the three classes. And that means 75 minus 58, which is 17, taking none. And so that number goes out there. How many students are taking math and Spanish but not history? Math and Spanish but not history? 3. Okay. Be careful about language when doing these kinds of Venn diagram problems. Which area goes with which statement? Don't put in the numbers until you've actually figured out how they get broken up in the Venn diagram. So those are addition principle problems, multiplication principle problems. I have 14 shirts and 7 pairs of pants. Can I go an entire semester without repeating an outfit? Right, an outfit is a pair of pants and a pair of shirts. Well, sure. I have 7 choices for pants, 14 choices for shirts. I have 98 different outfits. So I can go an entire semester without repeating an outfit. Suppose this sandwich shop, like Subway or something. Incidentally, if you want to see a weird problem, look online for how many sandwiches are available at Subway. It's a tricky counting problem. But at a sandwich shop, you have to, we'll change that to must, a very strict sandwich shop. You have to choose from 4 types of bread, 6 types of meat, 3 types of cheese, 5 types of mustard, and either carrots or chips. So how many different sandwiches plus a side do you have to choose from? So bread, you have 4 choices, meat, you have 6 choices, cheese, you have 3 choices, mustard, they like their mustard, so they have 4 choices, and a side, you have 2 choices. So you're making a sequence of choices. First you choose your bread, then the meat, then the cheese, then the mustard, then the side. So you're making 5 choices. There's different number of choices at each one, but you just multiply them all together, and that will give you the total number of possibilities. So 720 possible sandwiches in the side. If you're multiplying out things, which you do a lot of in algebra, how many different terms would you get here if you're doing the distribution and multiplying this out? Well, you can think of this as in terms of the parentheses. Distribution means taking one of these and multiplying by one of these and then multiplying by one of these. You've got 2 choices from here, either A or B. You've got 3 choices from there, C, D, or E, and then 4 choices from there. So after you multiplied that out, you should end up with 24 possible terms when you multiply that out. It's a nice way to double check your algebra sometimes. If you know how many terms you're supposed to have, then you can count them and see that you got them right. So again, multiplication principle, a sequence of choices, you multiply the number of choices at each step together. Okay. So 6-bit binary strings, that's things like 100, 101, right? Strings of 6 ones and zeros. So how many are there? You have to choose 6 things, right? And they all have to be the first one, the second one, up to the 6th. And you've got 2 choices for each. So 2 to the 6th, which is 64. So there's 64 6-bit binary strings, 64 different ones. How many start with 1? Well, if you start with 1, that means you've got 5 choices you can make. 1, 2, 3, 4, oops, there should be 5, to fill in the rest of the string. So there's 2 to the 5th. Same thing, we're thinking about starting and ending with 1. Got 1, 2, 3, 4 choices to make. You have 2 choices for each, either 0, 1 here, 0, 1, 0, 1, 0, 1. So that's 2 to the 4th, 2, 4, 8, 16. 2, 4, 8, 16, right? It's 16. So how many either start or end with 1? Right? The magical word or, start or end with 1. This is talking about cases. So you could have start with 1, There's 32 of those. End with 1. There's 32 of those. But you have to keep in mind that there are 16 that do both. Right? So this 16 is counted here and it's counted here. So how many do you have total? 32 plus 32 minus 16 is 48 strings that start with 1 or end with 1. Right? So an or, that's telling you this is a case. When you're dealing with cases, you have to make sure you subtract off the overlap of the cases. How many are all zeros? Well, there's just one that's all zeros. It's 0, 0, 0, 0, 0. How many have exactly 1, 1? F. Well, exactly 1, 1 means you have to pick 1, 2, 3, 4, 5, 6. You've got 6 spots. You have to pick 1 spot to put the 1 in, and then you have to pick, then fill everything else with 1. So you pick a 1, and then you fill everything in with 0, and that gives you one of the strings that has exactly 1, 1 in them. So how many strings have exactly 1, 1 in them? There's just the 6. At least 2 1s. At least is a tricky statement. So if we look at the possibilities, what are all the possibilities for all my strings? I can have exactly 0, or exactly 1, or 2 or more. Right? So those are my cases, my categories for thinking about strings. Right? Either I have exactly 0, or exactly 1, or exactly 2. So how many strings are there? We'll go up to the top. There's 64 strings total. That is, in that count of 64, that's 1 string that's exactly 0, plus 6 that's exactly 1, plus my unknown quantity, which is 2 or more. So 64 minus 7, this is 57 that have 2 or more 1s in them. And again, this is a complement, right? The complement of 2 or more is exactly 0 or exactly 1. There's 7 of those, so there must be 57 of these. When you see at least or at most, often that means you're talking about a complement.